I already made a video on an RC circuit, and I'm going to include that link down below. And in that previous video, what I did was to look at a battery connected to a capacitor and a resistor. We call this an RC circuit, and I solved it analytically to get the following expressions for the charge, voltage, and current. So charge as a function of time, the charge on the capacitor would be the VB. I'm using VB for the battery voltage. Some people use EMF, but times C times 1 minus e to the negative t over RC. VC is the voltage across that. Just take the charge divided by the capacitance. And then the current is VB over R e to the negative t over RC. So I went over all of that, and I don't want to cover it again because it's in the previous video, and I will link that down below. But I'm going to show you another way to solve this problem. And let's just get started with the loop rule. So if I say delta V, a loop, for a circuit is equal to 0. That's the loop rule. It says that if I start here and I go around the loop and add up the voltages, I have to get to 0. So let's start here. Let's imagine that this is the current going that way. The current comes out of the positive side of the battery, and this would be the positive side of the capacitor and the negative side of the capacitor. So if I do that, I go from here to there. I'm going from the negative to the positive, so that's going to be a positive VB, whatever that is. I'm going to use 3 volts. We'll talk about that in a second. And then I'm going to get up to the capacitor. I'm going to go from the positive to the negative side. So that's going to be a negative change in potential. And the potential across a capacitor is going to be Q over C. VC equals Q over C, where C is the capacitance of that, and Q is the charge on one of the plates, because the total charge is 0. And then I'm going to come down here. I'm going in the same direction as the electric current, so that means that there will be a voltage drop across that resistor of minus IR from Ohm's law. And that has to equal to 0. So in the previous video, I just wanted to solve this equation. Now notice here that since there is a current coming out of the battery, the charge is going to build up on the capacitor. So this is not a constant value. And since there's charge building up on the capacitor, these two things have to add up to this to be 0, but this is increasing, so the current has to decrease. So current changes too, which changes the amount of charge, the rate that charge goes on the plate. So it's not a trivial equation. Doing a little bit of tricks, we can get this in a way that we can integrate and find that, and then I can use that to find this and this. So that's what I did. And we're going to do this in a different way. And the very first thing we're going to do is to start with the definition of current. I is delta Q over delta T. It's the rate of change of charge. Now, in this version, I took this as a derivative, but here we're just going to use it as a finite difference. Delta Q over delta T. Let's put that into that equation up there. So I get VB minus Q over C minus R times delta Q over delta T equals 0. So all I did was take the expression for I, replace it with delta Q over delta T. And so, I mean, these are differences, right? If I take some time interval delta T, there's a Q at the beginning and a Q at the end, and that tells me the difference of the charge on that plate during that time interval. What the charge change at? And you'll notice, though, that here I have a Q and a delta Q. So that means that I don't have a constant rate of change on the capacitor, and makes things a little bit more complicated. But this is just a number. I mean, it looks like a derivative, but it's not. It's just delta Q. It just happens to be divided by delta T. So what I want to do is to solve this equation for delta Q. So let's add R delta Q delta T to both sides. I get VB minus Q over C equals R delta Q over delta T. Now I can multiply both sides of the equation by delta T over R, and I get delta Q equals VB delta T over R, and then have this is going to be minus Q delta T over RC. Now, suppose I pick delta T equals 0.001 seconds. And I actually know the value of the battery. I'm going to say 3 volts, the resistance, and the capacitance. I know all those things. And also I know that at t equals 0, Q of 0 is 0. I'll call this actually Q0 equals 0 coulombs. Then I can use this equation to find out the change in charge. I can solve this. I solved it for delta Q. I can put in 3 volts. Delta T is 0.001 seconds. R is 10. Q is, well, there's 0 charge on the plate. I'll put in 0. So that whole thing's 0. And I'll get delta Q. And then I can find, that's the charge at t equals 0. I can say Q1, the charge at the end of that time interval, is going to be Q0 plus delta Q. So this is the amount that charge changes. So if I add that to what the charge was, I get the new charge. And this is kind of a lie. It's a lie because this delta Q depends on Q. So the change in Q depends on the Q. So this is not an exact equation because is this the Q at the beginning or the end of the time interval? And the answer is neither. But, so it's a lie. But if delta T is small enough, then, and delta Q is small enough, then I can approximate Q as not changing during that time interval. And so it's a lie, but it's a small lie. Okay, so I can use that, calculate delta Q, and use that to find the Q1 after 0.01 seconds, 0.001 seconds. And then I can do it again. I can find the time after the charge after the next 0.001 seconds as equal to Q1 plus delta Q. But in this case, right here, I'm actually using Q0 right here. And right here, I'd be using Q1. So I'm going to recalculate delta Q and then find the new Q2 and then keep doing this forever, or until I get bored, or until I stop, or until I want to stop, whichever one it is. So this is the basic idea of a numerical calculation. Break the problem into small time steps, and during each time step, make some assumptions about the values over these things. So here's how we're going to do this. Number 1 is we're going to calculate delta Q. We're going to start with initial conditions. Calculate delta Q. 2, use that to update Q. And then 3, T2 equals T1 plus delta T, update time. And then do the whole thing over again. So if I wanted to model this for 1 second, I would need to do 1,000 of these delta T's. So I need to do this and this. I don't even really need to do that 1,000 times. I don't want to do that. So I'm going to instead make a computer do it. So there's nothing inherently required for this in a computer. It's just that it allows us to do things that we don't want to do a whole bunch of times. Okay. So let's jump over. We're going to do this in Python. And now the other important thing is I'm actually getting numerical values for this. That's why it's called a numerical calculation. So I need numerical values for stuff. I can't get an analytical expression, but I will use those same values in these to make a comparison just so we can see how things work. Okay, so here we are going over to Python. There. Okay, so I'm using GlowScript VPython. This is an online version of Python with some built-in stuff for graphing and vectors and stuff like that. And I'm not using vectors. I'm not making any 3D animations, but I am going to use the graph. So that's the first thing I want to do is to set up my graphing. And if you don't know what this does, it's not a big deal. I'm just going to do it. But I'm going to put in a few lines of code just to set up the graph. And I'll run it so you can see what it looks like. So the first thing is to make a graph. I'm going to call it G1 is the name of my graph. And it's going to have, I want to plot charge as a function of time. So the X title is going to be time in seconds, and the Y title is going to be equal to Q in coulombs. Okay, now one other thing, I'm going to set the width and the height. So I'm going to say the width is, let's say 450, and the height is, let's say 220. And that's just going to make the graph smaller so that it'll appear on the window when I zoom around. But if I do that and run it, nothing really happens because I didn't do anything. Okay. So next I need to actually add a curve to my graph. And I'm going to call that, let's call it FQ. Let's call it F1. F1 is an object called a G-curve, and I'm going to give it a color, make it blue. Now, will it make a graph yet? No, it still doesn't. Okay. So just if you haven't seen this before, f1.plot, I can give it an x and y coordinate, let's say 1, 1, and run that. And then you can see there's my graph. It only has one data point on it, and so it's kind of right down there. It's kind of boring, but that's how graphing works. And if you want, I have a video on graphing. I'm not going to focus on that, but if you want that, let me know. If you can't find it, I'll find it for you. Okay, so all I do is set up the graph. Next, I'm going to set up all my initial conditions. So let's see, VB is 3, R is 10. Notice that I'm not putting units over here because it's a numerical calculation, so Python needs it as a number. If I put a V there too, it's not a number. So I can put the units here if you want. I'm not going to because I'm a lazy person. Q equals 0, C equals 0.5, and you can change these values. I think, and now Q equals 0. We'll get back to that. R, C, T. I need T equals 0 and DT equals 0.001, just like I said. Okay, let's just make the simplest plot. What I'm going to do is say while T is less than 5. So this is going to keep changing everything in this loop until T is equal to 5. What I'm going to do is just plot Q versus T. So just so we can see how it works. F1.plot. The x coordinate is going to be T. The y coordinate is going to be Q, which is still 0. And then I need to update time, right? If I don't add another line, this will just go on forever because T is 0, which is less than 5. So just keep on forever. So I can say T equals T plus DT. Now, if you haven't seen this before, you may say, oh, the T's cancel. They don't cancel because this is not an algebraic equal sign. This is a make equal to sign. This says take the value of T, 0, add DT, 0.001, and then make that the new value of T. So I don't have to keep track of T1, T2, T3. I just say T and it changes. Okay, let's run this. And there's my graph, 0. Okay, so we're all cool now. Okay, so that's my graph. But what I want to do is to, like I said, number 1, calculate delta Q. So I'm just going to call this DQ. And what I'm going to do now, I'm looking over my paper right here. And I'm typing in the equation just like I see it. So delta Q is VB times dt divided by r minus q times dt divided by r times c. Make sure you put the parentheses, because if you do divided by r, it's going to divide by r, and then it's going to multiply by c, so that's not the same thing. And you notice that this does depend on q. I need to know what my value of q is. It starts off at 0, just like I said. Now I'm going to use that to update q. So q equals q plus dq. Just like I said, updating q. And then that's it, right? I plot that value, and then actually let's put this plot down here. It doesn't really matter if delta t is small, but I like it down here at the bottom. So f1.plot tq. I'm going to plot it versus q. Oh, I did have q. Okay, that's it. I think that's it. Let's just run it. Okay, so there you see the charge increases with time, and it reaches some, looks like it might reach some maximum value. Let's see if we can find out where it gets to maximum. I'm just going to increase this to, let's say, 30 seconds. And there you go. Now, that gets a maximum of 1.5 volts. Is that what it should be? Well, yeah, it should be. So if I have a total voltage on the capacitor at the end would be 3 volts, and it has a capacitance of 0.5 volts, then Q is equal to C times V. So V is 3 multiplied by 0.5, I get 1. Okay. Let's go ahead and plot the theoretical value of Q just to see if it's the same. So I'm going to go down here and say F2 equals G curve. I'll give it a different color. Color equals color.red. And now I need to calculate that theoretical value and I'm going to plot that. So let's go down here and say QT for theoretical. And now I'm looking at my equation that I wrote down before. It's VB times C times 1 minus the e to the negative t divided by r times c. And this is not an update. This is an exact calculation. But now I can plot that f2 dot plot t qt, and let's see what happens. And you'll notice that, oh, I just realized my picture's covering up part of the thing. Sorry about that. You'll notice that it looks like it's just a red curve, but it's not. It's actually a blue and a red curve. They're just right on top of each other. Let's see what happens if I make a ridiculously small time interval or large time interval like 1. Now you can see that I get slightly different answers, but it's still a pretty good answer. Okay, and that's because I'm using that assumption that Q is constant during that calculation of delta Q, and it's not over 1 second, but it gives me pretty good values. You can just change this to 0.1, and you see that you can barely tell the difference between those two. So 0.01, it should be fine. And so it works. Okay, but now what about the current as a function of time? I want to plot the current as a function of time. Let's do voltage. That's pretty easy, right? So I can go down here and let's change this to V, just to be VC in volts. And then down here, I need to calculate that. I can say VC equals Q divided by C. That's how we define the voltage across the capacitor. I just calculated charge. I know C, so I can calculate that. Let's calculate VT. It's just going to, it's the same thing. It's VB times 1 minus exponent negative T divided by R times C. And then let's plot what did I call it? VC and then VT. And it should look basically the same thing. But you'll see now it gets up to a maximum voltage of 3 volts, which is what we expect. Everything's working fine. But now what about the current? The current was a different formula. Well, down here, I can actually calculate the current, right? The current is defined as delta Q over delta T, so let's just calculate that. I equals dQ divided by dt. Now let's also calculate the theoretical. IT is going to be equal to, I'm looking at my formula here, VB, it's VB divided by R times exponent negative T divided by R times C. And let's plot those. IT, and capital. And I have to go up here and change this. I will get in trouble with the unit police if I don't. Let's say I in amps. And run it. And I messed up. Can't find T. I. It's okay to make mistakes. Bam! Check that out. And again, those two curves are right on top of each other. I'll just prove you that that is indeed the case, like that. And you'll see that there is a slight difference. One of the things, too, if you want to see the two graphs, you can do this. 0.001. Down here, I'm just looking at the difference of 0.05, looking at the current, and I'm going to say, I'm going to plot IT plus or minus, no, let's say plus 0.01. Let's just see what that happens. So I'm going to shift it up a little bit. And there you can see that there is that doesn't look right. It should be shifted. What if I get rid of that? I mean, I guess it looks that way. Yeah, I think it just looks that way. But that way you can see that there is a difference between those two. And there you go. So this is a legitimate way to solve this problem compared to the analytical solution. Some might think this is more intuitive, and I kind of think it is more intuitive. It's also legitimate. There are some problems that you can only solve this way. And this allows you the flexibility to do things like, what if the resistance changes? What if it's an actual light bulb and the resistance depends on the current? So as the current increases, the resistance increases. That's possible. You could put that in here. It wouldn't be too hard. Or what about this? What if it's not a constant voltage battery? Well, if it's oscillating, I can calculate the voltage of this battery as a function, just recalculate it every time. It'll work. And I'll do that in a later date. But this is your just plain basic RC circuit. And I'm going to give you the link to this code down below. The link to the previous video where I do it analytically down below. Hope you find that useful.